And we're back. Welcome back from the weekend. And today we will pick back up with the balance of our discussion on processes. Today, focusing on actual examples of interprocess communication, as well as a little bit more detail about the mechanisms for accomplishing interprocess communication. But before we begin, some administrative bits. Of course, the reading has changed by October 6th. Pages 106 to 145 with the section 3.1 through 3.8 in the OS concepts text, due on the 29th of September at the usual 1 second before midnight. Project number 1 on palindromes. So where we last left off, we talked about synchronization, and we said with respect to IPC, or interprocess communication, you can have non-blocking sending of data, where the sender sends the message and continues on, and then is later notified with a response. With your non-blocking send and your non-blocking receive, the receiver receives either a valid message or a null message. And there are different types of combinations possible, but if both sender and receiver are blocking, that's called a rendezvous. So that means the receiver waits for the receive call to finish, so it blocks, and the sender at the same time waits for the send call to finish before continuing. So that means they're both there physically at the same time in order for that communication to go across that channel. So let's turn our attention to examples of IPC, interprocess communication systems, on the Unix side, specifically POSIX. And one important one is shared memory. And with shared memory, as the name implies, it's a block of memory that sits and remains and is in memory, and more than one process can access it. One can write information to the shared memory, and the other will read information from the shared memory. And so in doing this, first a process comes in and it creates that shared memory segment using a command, a system call called SHM open, or shared memory open. You give that shared memory a name, a text name, so that another process can be embedded with that name and then refer to it and attach to it and read and write to it or from it. So you give it a name, and then you give it permissions about what you want to be able to do with it. In this particular case, you OR together a binary OR, these different commands, and these are defined in header files to create the shared memory, and in this particular case, to read or write the shared memory. So that's on the creator side. And this last mode bit talks about the permissions that the process requests is associated for both the user, the group name to which that user belongs, and everyone else credential-wise on the system. So this is also used not only to create, but to open an existing shared memory segment. And so then next, you set the size of the object you want to store in shared memory. And this is ftruncate, and you give it that shared memory file descriptor. So it's treated like a file. It's not really a file, but it's treated like a file. And as such, you can actually view the contents of shared memory, because Unix will maintain a special file system to which it associates things that are in shared memory. So you can actually read it and write it and take a look at it. So you can set the size of this object, shared memory, through ftruncate. You give it the file descriptor, and then you give it the number of bytes for that particular part or region of shared memory. So now you can either write to shared memory with sprintf, some data, or you can read from shared memory. So here's an example of a producer that's going to populate memory, shared memory, with data. We start out here and we set a size and we set a name. In this case, the name is going to be OS. We have two messages, hello and world. And then we create a variable for our file descriptor. And then we set a pointer to nothing, a void star, so it can point it to anything. So we start out with SHM open to create that shared memory. We give it that name, OS, which is stored in that name pointer. It's a character string. We want to create it and also make it readable, writable. So the producer is going to write into shared memory. And then we have this permission for read-write for the user, for the group, and for everyone else. So now we enforce a size of that block of shared memory. So we ftruncate, as we said before, using that size variable that we defined earlier. And now this mmap is particularly important. What mmap says is now that I have the shared memory, I want to create a pointer in my local program, but I want this pointer to refer to the memory location that has been carved out of memory for sharing with another process. So that's what this mmap does. So I give it a size, I give it an operation I'm going to perform on it. I'm going to have the read permission turned on. It's going to be shared, and this is the file descriptor. And the other parameters, I'll leave it to you to look up in the manual pages for the system call. So then here, with this sprintf, that's why I'm going to write that message 0, hello, into that shared memory referred to now by this pointer that I got when I mapped that memory into this pointer to be accessible by my process. And then I increment that pointer to move to the next memory location that comes right after the length of this 0th message, message underscore 0. So then I write in the next message, message 1, hello. So this will leave hello world in this shared memory location. So this last part is particularly important. My process exits. I return 0. And so now that process exits or terminates, but what is left behind is that piece of information, hello world, in shared memory. So next, we have another process that comes along, the consumer. Now, it has encoded in it the name associated with that piece of shared memory and the size. So what does it do? It opens that shared memory, SHM open. So then it gives the name, so it knows, the kernel, which piece of shared memory we're referring to. And RD only for reading only with the permission, 666 for user read write, group read write, everyone else read write. And now we take that shared memory block and we associate it with a local pointer in this particular process, the consumer. We get that memory, and you notice it's a certain size. It's the same size we had before, so that amount of block of memory is going to be read-only, shared, and there's the file descriptor that we got from opening by name. So it's that name that is the link to that same piece of memory, even though this process, the consumer, didn't exist as a process in the system until after the producer has terminated. And then we're going to print out this memory. And so here, you're going to see a message. You don't see that message anywhere inside the consumer. It's not encoded. It was placed in memory, shared memory, by the producer. So let's take a look at this in Linux. We will exit the PowerPoint momentarily, and I will meet you in Ubuntu Linux. So we're here in Ubuntu Linux. Let me log in to my desktop. And I have here, I have two windows. And in the window on the right, I'm going to do a little bit of lookup of things. In the window on the left, I'm going to do the editing of my program. And so I've taken the liberty to write a bunch of C files. We have demo 1, demo 2, and demo from before, but we've added producer.c and consumer.c, which are exactly those programs that we discussed in the PowerPoint. So let's go first into the make file. And I'm going to add rules in order to make producer and consumer. So I add a default rule for producer and consumer. And then I'm going to add a rule for the linking of producer and for the linking of consumer. So I'm going to add a line here. My target is going to be producer, the executable, and that's going to depend on the object file producer.o, which is the result of compiling producer, rather that executable is going to depend on producer.o, and it's going to be the result of linking. So I'm going to say GCC-O. The output of linking is going to be called producer, and it's going to paste in object file producer.o. But at this juncture, I'm not done, because for producer, it's going to use those shared memory routines. And so I'm going to add in a library to this, and that's going to be that library called librt. So I say -L, include in system library, librt, and I just have the RT part here. So that's going to be my link for producer, and let me do my compilation. So I say my target is producer.o, and that's going to depend on producer.c, and I'm going to compile GCC-C compile producer.c. So I'll do the same thing for consumer. So we have consumer. That executable depends on consumer.o. I link gcc-o to produce consumer. I paste in consumer.o, that executable, using the library-lib rt. All right, so now I need consumer.o as my target. It depends on consumer.c, and it's accomplished by gcc-c compiling consumer.c. But I'm not done yet. If I clean, I want to remove producer and producer.o, likewise consumer and consumer.o. All right, so let's test this out. We clear, and I'm going to now call make, and we see the make happen for my producer and my consumer. And so now I'm going to run my producer. Let's show you the producer code first. Producer.c, and it's exactly what I went over in the PowerPoint. We create the size, we have the name, we come down, we have the creation of the shared memory, we configure the size, we map in the pointer, and then we do the sprintf of that message. Okay, so now let's go to consumer.c, and you see nowhere in this program do we define the message. We're going to get that message from shared memory. So we open that shared memory, we map it into our local address space, to that pointer, and then we go ahead and we print out what that pointer refers to. So we're accessing memory. And this last part, we unlink shared memory. We're removing the existence of the shared memory. So let me type make again. And there are some commands that are pretty neat commands on the Linux and Unix command line interface that allow you to view the different types of interprocess communication mechanisms. It's called IPCS. And if you look in the manual pages, I direct your attention to the window on the right, man IPCS. It allows you to view information associated with all of the interprocess communication mechanisms. Those are shared memory, those are queues, there are semaphores that are on your system. And so if I run IPCS, it'll show you, among other things, the message queues, we talked about that, semaphores, we haven't talked about that, but shared memory segments. And one of the things it'll tell you is who the owner is of the shared memory segment. Now, in Unix, everything is treated like a file, and there's a special file system called the device file system. And this device file system, underneath the covers, the kernel presents different pieces of your system as if it were a file. Now, you might wonder, well, why is this useful? It's useful because it offers a single interface with which to access all parts of your system, be that the disk, the network card, and even shared memory. And so while shared memory is not a file, it's not on disk, it's treated like a file in terms of your access to that piece of shared memory. As such, there's a directory called dev shm, and inside of shm, it'll have a file associated with each block of shared memory that has been allocated to the system. And so here you see POSIX, and some of these are owned by OSC, the name of this account, operating system concept. Others are owned by LightDM, that's part of your kernel. And so there are all sorts of processes on the system making use of shared memory. So shared memory is a very important concept and a very important mechanism for processes to coordinate with one another on the same machine. So let's go ahead and run that producer. And to remind you, if I look at the producer source code, we call the name of that shared memory OS. So now we're going to run producer, the executable, and it's going to create that shared memory, and it's going to store the text hello world in that shared memory. So now if I make a listing, ls-l, dev, device file system, shm for shared memory, we notice here we have an entry that's 4096 bytes, and it's created by OSC account. Now you notice it's read write, read write, read write. So the permission 666 that we had in the source code. And this text file or this file inside of the dev SHM directory, if I were to look at the contents, you would see exactly that data that was written by the producer. So let's do a cat command. And what cat does, it shows you the text. If I were to type cat producer.c, all of the text of producer.c would come swirling by. So let's clear the screen. And let's look at, again, that shared memory directory. And so now let's do a concatenation of dev SHM OS. And if we do that, you see hello world. And so, yes, absolutely, hello world is in our shared memory. So now we're going to run the consumer. To jar your memory, the consumer, it doesn't have that text anywhere. It only opens your shared memory, maps that shared memory to be accessible by its process for the consumer. You use in the form of a pointer. You use that pointer to then access that content of shared memory and print out that message. So let's go ahead and do that. Now, the interesting thing to pay attention to is at the bottom here, before exiting, this consumer process in its main routine, it does an SHM unlink. And that SHM unlink is to remove that shared memory object. Because if you don't explicitly remove it, it'll remain sticky, if you will, and stay around in memory. So again, if we ls-l, do a listing of this shared memory directory, we see that shared memory segment. And it's 4096 bytes, and it was created by OSC process. So let's run the consumer. And the consumer accesses it and prints out hello world. Okay. If we tried to run the consumer again, remember the last thing the consumer did was detach and free up, as it were, this shared memory. If I run it again, it crashes because it's trying to access something that does not exist. So let's verify that, and let's look in our shared memory directory, and we notice it's no longer there. It's gone. It has been deleted. Okay, so that's an example of shared memory. It's immensely useful. Our producer creates that shared memory. Let me write producer and run that again. And when we do that, we find that shared memory has been created and exists. And then the consumer accesses it, prints it out, and then deletes it. And now it's gone. All right, so with that, let's go back to the PowerPoint, and I will meet you in PowerPoint. So those were some examples of inter-process communication systems, specifically shared memory. So let's look at communication in client-server systems. And so a client-server system is a way of structuring your computation, and this computation involves two entities. Let me set my pen. I'll set it to blue. One entity or process is called the client, and the other entity or process is called the server. Now, the client is that entity or process that initiates the interaction. So it sends some message, and that message is typically some kind of request. So it's a text, or it can be some binaries, and it's understood that this request encodes something that the client wants the server to do. So the server receives this request, it does something as a result of this request, and then it returns response. And this response is sent back across the communication channel, and the client gets this as the response. Okay, and so there are different ways of doing communication system when you structure your interaction between two cooperating processes in the form of this client-server approach. There are sockets, which is a construct. It's a software mechanism that is used to represent this channel of communication, this interaction between the client and the server, the so-called remote procedure call. And with the remote procedure call, it's a machinery that performs this interaction on your behalf, but from the perspective of the client, it looks like a function call. And there are pipes, which is a mechanism for two processes on the same machine to communicate. And then there's RMI, remote method invocation, which is RPC over Java. It's unique to Java. And so let's look at sockets. A socket is defined as an endpoint for communication, and it consists of two pieces of information, a so-called IP address for Internet Protocol address, and that IP address uniquely identifies the machine or host with which you're communicating. And every host, and more correctly, network card, has a unique IP address. So this is how you identify this notion of where do you want the message to go, what machine. And then the port number, that port number identifies the particular process. So between these two pieces of information, we know where it's going to go and to what executing program it will be delivered once it gets there. And so this information is included at the start of this unit of communication, a so-called message packet, and that's how you differentiate which service on a machine is going to be the target of this interaction between the client and the server. And so, for example, this particular number, 161.25198:1625, refers to process associated with port number 1625 on machine associated with IP address 161.25.19.8. Now, if you take computer networking in the spring, CSCI 330, we will go in great detail about how the underlying plumbing and protocols that allow you to be able to do this. But that's beyond the scope of this class. So with a socket, the communication then is not merely between the client and the server. It's really between the client-side socket and the server-side socket. So the client-side socket is going to send to the server side is going to send back the response. So that means you can have more than one channel of communication, either between the same two machines, as is the case here, or your client can talk to different machines at the same time. Here's another server number 2, and say this is server number 1. There's also a special IP address called the loopback address, and it's an address of the form 127.0.0.1, and that refers back to yourself. So if a process on your client wanted to use a socket to communicate to another process on itself, it's going to use that special address, which is this so-called loopback address. Now, these port numbers are special. Port number values that are between 1 and 1024 are used for standard purposes like email, like your web address. And so, for example, your web address, the port number for web servers is port number 80, and that's for so-called hypertext transfer protocol, or HTTP. Now, again, we cover this in great detail in computer networking, so I'm not going to go in that same detail. That's not the purpose of this course. All right, so when we have our socket communication, we have our socket, our tuple, consisting of the IP address, that's the IP portion, and the port number. So we're identifying some process running on this particular machine or host. We're calling this host X. And so that creates a channel of communication, and it's bidirectional to another socket on, say, your web server. Now, you notice here the port number is 80 on this other machine identified as 161.25.19.8. And so there are different types of sockets. There are so-called connection-oriented sockets, and these give you reliable delivery of your message data. And there's connectionless that is unreliable. Now, you might wonder, why would anyone want unreliable delivery of data? Because it's faster. Reliability is slower. So you're trading off speed against reliability. There's another type of socket or channel of communication called multicast. And what this multicast socket does is it allows your client to send one message on its side, but underneath the covers, it's sending that message, getting delivered to one of some number n of machines out there. And it's managed by something called the multicast group. And this multicast group manages the construction of this tree so that you as a client only send that message once to that socket, but it gets delivered or sent to more than one receiver, and that's called multicast. Now, sometimes, and you see this in Java, a single connection on a socket is often called unicast, but a multi-connection is called multicast. Okay, so let's think about a date server where you're going to ask it as a client, you're going to say, give me the date, please, and the server is going to see that, look it up on its internal clock, it's supposed to be a clock, and then send back a response with the date is, whatever that date is, day and time. And so this is an example in Java. So this is the server, and it's going to respond using this server socket. And the server socket's whole purpose is to wait for incoming connections. So you create a server socket, and you associate it with a port number. So the process that runs this main entry point is going to be associated with this port so that the system knows how to identify the server process in order to deliver messages and to know where those messages came from. So it sits in a tight loop. So here's our while block. And it says, okay, on this server socket, this welcome mat, as it were, it's going to accept an incoming connection. And for each incoming connection, it creates this client socket, and it's going to use the client socket to interact with the client. So on the server side, when it gets the output stream to write to this socket, client socket, it's sending data across the wire to the client. So the server, it accepts an incoming connection, it gets the output stream from that client socket, it wraps a formatted writer on that output stream, and it calls it P out, and it's going to use that to write information, i.e. responses, back to the client. So when it gets that message incoming from the client, the server, what does it do? It takes that print writer, it writes down that output stream, the result of getting the date and time across the wire. So this print writer is used because it's convenient, because it looks just like printing, only that printing is redirecting out through the client socket, representing the server-side connection to that client who has submitted an incoming request. So then after that, it closes the client socket and the server is done, and it goes back to the while loop again and again and again, accepting incoming requests and sending out dates as a response of that incoming request. So this is the client. So the client then creates a socket, and we're just going to assume that these two processes are running on the same machine. If they weren't, this would be an IP address that's different from the loopback address, and it has this port number 6013. So what does the client socket do when this socket call or this instantiation of a socket object is complete? You have a connection, and so for the client to receive responses from the server, it needs the input stream. So it gets the input stream from this client socket, this connection to the server, and then it creates a reader, a buffered reader, to get that input stream, the data from that input stream. So this is going to be the plumbing for the client to get response from the server. So now that we can do that, well, the client is going to get that information from the socket. So it's going to take that buffered input reader and actually read it and print it out. Okay. And so you create the socket connection. The request is sort of a null request. Just by creating a connection, the server is going to see that connection request, and it's going to send the date across. The client reads the date from the server, that response, and then the client closes its side of the socket. Okay. So another version we talked about, we said remote procedure calling. And remote procedure calling is the masking of a client and a server through a function call. So to the client, it looks like a regular function call, but underneath the covers, there's support through the kernel and through some APIs to actually make a network call across to a server, and the server performs that function as if it were a request from a client, and then returns back the response, and then that return value is sent back to the calling function, the process that called the function, and it thinks it was a function call, but really it was a client sending that data across the network to a server, getting back the response. So we have our two entities. We have the client side and we have the server side. And this support includes the kernel because the kernel is going to do some stuff on your behalf. And so we start out, and we have these two entities. One's called the client stub, and one's called the server-side stub, or the skeleton. And so here we have our client, and it's going to call a function. And this function is associated with a stub. And to the client, that just looks like a normal function call. So you just call a function, and that function returns back a return value to you. But underneath the covers, this client stub is interacting with the kernel to package up the parameters of the function as well as the name of the function as information, a packet that can be sent across the wire in the form of a socket. So now that's sent on your behalf, and on the server side, their incoming request comes in to the kernel side of the server side kernel, and then it says, oh, wait a minute, which function were you calling? Let me look in my special library of functions that are implemented as remote procedure call implementation. And I'm going to call into the skeleton, the server-side stub. It's going to unpack that information, call some local server function, get back the response, send the response back down to the stub, packages it back up, goes to the socket on the server-side kernel, sends it back. It's received by the client-side kernel, sends that up to the client stub, unpacks it, and gives it to your function, your caller, as a return value from that function. But to your local process on the client, it looks like a function call, but underneath the covers, all this plumbing, the sockets on the client side, server side, the stub on the client side, the skeleton on the server side, they handle all of those details of packaging and encoding and unpackaging and decoding and calling and returning back results. And so we have these stubs. These stubs act as proxies that perform the network parts on your behalf, you're being the function called by that process on the client. And so the stub has a bunch of responsibilities. It locates the server by its name, and then it takes the parameters and packages them up, called marshalling, and then it sends them across the wire. The server-side stub receives this information through the server-side client, server-side socket. So the server then unpacks them or unmarshals them, makes a local call, and then sends back the results. The reverse operation happens. And so on Windows does remote procedure calling, RPC. The stub code is created. You define an interface, and the interface tells you the names of the functions, the parameters and types the parameters take, as well as the return type and the number and how the return, what the return value is. And so all of this is defined when you write your program. And in Java, you pass it through RMIC, the Remote Method Invocation Compiler, and it generates the server-side and client-side stubs, and then you just complete your implementation. On Windows, it's the Microsoft Interface Definition Language, and you have a compiler for that that's going to produce the stubs for your client side and your server side. So remote procedure calls have a data representation, and this is often called in literature the wire format, because if you're going to make a procedure call on one machine, and let's say that's running Linux on Intel, and you're going to call to another machine that's maybe Linux running on the ARM processor, you might have different architectures about how you represent data, whether you represent the most significant bytes first or the least significant bytes first, big endian or little endian. And so you need a common representation called external data representation, and this is your wire format. What does an integer look like when it's transferring across the wire over that channel of communication? And one of the big caveats to pay attention to is, yes, absolutely, when you're doing remote procedure calling, you have your client and your server, and from the client's perspective, it's calling a function, and it's getting a return value. But because underneath the covers, it's actually using a socket mediated by the kernel, these things can fail. Your network can time out. And so remote procedure calling and remote communication in general has more ways it can fail than if the two processes were communicating through some shared memory or some other process to process on the same machine type of communication. Moreover, let's say if the network kind of has a hiccup and you resend it, well, the semantics are called idempotent. Idempotent. That means at most once. If you call a function, you only want that function to happen one time, right? And so it's a lot more tricky when you do this remote procedure calling because it's important to try to react to the different failure modes, but also ensure that you're only executing this once. Because imagine if this was the ATM and you said withdraw $5. The network stalled and all of a sudden it was retried. Well, what happens? Do both of them go through? And if both of these happened, these retries of the sending, that would mean on the server you subtract $10, but on your account it says you only took out $5. So there's a problem there. So there's a whole field, distributed systems, where you look at these issues about how to react to these failure modes and how to deal with this at most once semantics, idempotent. And so operating systems typically provide a matching service that identifies which services to connect to in order to direct certain implementations of these remote procedure calls. Is it on this machine or is it on that machine? Which process is going to be the incoming recipient for a particular procedure call if it's on the same machine? So here's an example of the interaction between the client and the server from the perspective of what messages transport or traffic back and forth across the wire. So the user calls into the kernel to send an RPC message for some procedure. It's identified by name, and the kernel sends this message to the matchmaker using a standard port number for the matchmaker service on the destination server. So you have your message from the client to the server. Those are the addresses. It knows what port to use for the matchmaker, and it's regarding, give me the address of who I should contact for this particular procedure call for X. So the matchmaker gets this information, it unpacks it, looks up the answer, and says, aha, you want to use this port number P when you want to execute that procedure call for procedure X. So it sends that back across the wire from the server to the client for the kernel port on the client side, recipient machine. It says, oh, for this RPC call, identified as function X, you want to use port number P. So the kernel gets this and then places it in the message that's going to be for RPC. So now it knows which particular process on the server to contact for that procedure call for X. It then sends the RPC call. So that source is the client machine. It goes to the server. It knows the port number, so it knows what process or server process to execute on the destination machine. And then here's the content of what the parameters are for that procedure call X. So you have a process sitting in the background called a daemon, and it gets this response, and it knows which function to call because it's associated with port X. It receives the message, unpacks it, performs the request, and sends back the response. So the response goes back across the wire to the kernel on the client side. It delivers it to the user, and the procedure call has completed. Another type of RPC mechanism is so-called pipes. Unlike a socket, a pipe is typically between two processes on the same machine, and it acts as a type of channel or conduit that allows them to communicate. Now, some of the practical issues for pipes: do you allow unidirectional, one direction, or bidirectional, two-directional communication? So when I say directional, here's process P1, and we have process P2. Is it in one direction, or P1, P2, do we allow that communication in two directions? Is it half duplex, or is it full duplex? If it's two directional, do you allow both to communicate at the same time? Or is it only one at a time in one direction, but that same channel can accommodate either direction? Does there have to be a relationship between the two communicating processes? Does there have to be a parent-child between the two communicating processes? And so pipes can be used over network. Well, can they? Absolutely, you could have network pipes, but that's going to require a little bit more machinery in order to do that. And so Pipes are used all over the place, more specifically on the command line. If you were to concatenate the contents of a text file, well, cat is the concatenate command at the command line interface. You give it the name of a text file, and all of the text file contents will go whooshing by the screen. Now, if you use this pipe command, this is vertical bar, that says take the output of this process and send it to the word count process, counting the number of lines. And so let's segue back to Ubuntu and test out these pipes. So we're back in Ubuntu, and let's log back in, operating system concepts, to our window. And we're going to go on the left-hand side to that window. And remember before, when we talked about shared memory, I said cat producer.c. Now that's going to concatenate all of the contents of the text file. If I go to the manual pages on the right, man, cat, it says concatenate files and print on the standard output, which is the screen. So if I say cat producer.c, enter, it's going to give me the contents of producer.c. So now on the command line, that cat command is a process that is run by the command line interpreter. So if I said cat producer.c and now pipe vertical bar word count -L for give me the line count, now instead of whooshing by the screen, it's going to send the output of one process, the cat process, to this word count process. And if we were to look at the word count process, man word count, it's going to print all sorts of information about the words, like the number of words, the number of characters, or the number of lines if I use -L option for word count. So if I type cat producer.c, word count -L, it gives me 45. There are 45 lines in this producer.c file. So that's an example of pipes. So what happens is that we have two processes that were created by the command line interface. The first process was concatenate. Second process was word count. It took the output of one process, producer, the cat command, cat process, and it sent it as input to word count. So that's one of the things you can do with pipes that's really powerful, is redirect the output of one process as the input of another. So let's go back to PowerPoint now, and that's an example of using pipes. So there are two types of pipes. One's called an ordinary pipe, and these cannot be accessed outside of the process that created it. Now, we said that a parent process, when it forks itself to clone itself and create a child, it creates a duplicate. And one of the things that is duplicated is that pipe structure, and that allows a parent process to use pipes to communicate information to coordinate with a child process. And so that's one type of pipe called an ordinary pipe, with processes that are involved in the transfer of the information or the coordination by sending data through the pipe must have a relationship. That's an ordinary pipe. A named pipe can be accessed without this parent-child relationship, so that means it's intermediated by the operating system kernel. So an ordinary pipe allows communication in a standard producer and consumer style. The producer writes to one end of the pipe, the write end, and the consumer reads from the other end, the read end. So ordinary pipes are unidirectional. So we have this pipe data structure, we have our parent process, and that pipe takes the form of an array of file descriptors. There's one part of the file descriptor, two of them, one position that corresponds to the write end. That's always the second position, which is array index 1 in this array of file descriptors. And then the other end is the read end. That's always the first position, which is index 0. So this array of file descriptors, FD, has two elements, the 0th position and the 1st position for the indices. And the 0th index is the read end, and the first position, the 1st index, is the write end. And so the parent, it reads messages from the child through the read end, file descriptor 0. Let me select my pen. So the parent reads through file descriptor 0 and index 0, and it writes at file descriptor index 1. Likewise, the child is going to read file descriptor index 0. That's how it gets information from the parent process, and it writes to file descriptor position or index 1. So ordinary pipes require a parent-child relationship in order for the two processes to communicate. Now, Windows, it has ordinary pipes. Ordinary pipes is a Unix system, but in Windows, it's called anonymous pipes. And so there are examples, Windows code and Unix code in the book, and I encourage you to look at it. There's lots and lots of source code available on the web for examples and videos on YouTube as well. So this is an example in Unix of using pipes. So a parent process is going to fork, it's going to clone itself, but the first thing it's going to do, it's going to create an array of size 2, and it's going to contain 2 integers for our file descriptors, and it's going to call this pipe on that file descriptor array. And so that sets up the pipe. And so that pipe has the plumbing necessary for the read end, which is the 0th position. So we have a preprocessor definition for 0, and the write end, which is preprocessor definition 1. So whenever you're the parent or the child process and you want to read, you're going to use the read end indexing into that file descriptor array that was created as a pipe, and the write end anytime you want to send information to the process on the other side. So we start out, we fork the process, and after some error checking, if all goes well, you're going to have in this first block, that's going to be the parent process where it executes, and the clone, that is the child process, that's going to be this block. So the first thing the parent does, it's going to close the read end because it's not going to use the read end. It just wants to write information that it's going to send to the child. So then it takes the write part, the write end, or the write file descriptor for writing, position 1, write end, and it's going to write to that some message, and it tells this write command how many bytes it's going to write to this file descriptor. And then after it's done, it closes the file descriptor. Meanwhile, the child process is going to close the write end for the pipe on its side, and it's going to read input from the read end for its side of the pipe. And it needs to know how much to read, so it has buffer size, so that the read system call knows how much information to get from that file descriptor corresponding to the read end of the child side of the pipe. And then it prints out that message and closes the read end. So there we go. We have communicating processes. So you can imagine if you structured, say, your browser, and you had one process in your browser that was responsible for getting from the network all of the HTML information, and then another process that was a child process that would draw information on your screen. So this original get from the network process in a browser architecture might spawn a child process by forking itself and then communicate all of that HTML for your web page through a pipe one way to the child, and it would then just draw on your screen what your web page is, for example. And so pipes are a great way for two processes, and the key is on the same machine, to coordinate with one another instead of using something like a socket or remote procedure calling. And so another type of pipe, name pipes, they're more powerful than the ordinary pipes, and they're called name pipes because they're associated with a name. And because they're associated with a name, as long as the processes on a machine are in possession of this text name, they can communicate, so they can read or write to or from this pipe. So communication on a name pipe is bidirectional, but because of this name and this mediation of this name pipe channel or data structure through the operating system kernel, no parent-child relationship is necessary between the processes that want to communicate. Moreover, it's not just two processes that can communicate. You can have several processes that can use the same name pipe to communicate. And so if you have process 1, process 2, process 3, all on the same machine, you have the same named pipe, and now they can all communicate. Process 1 can write something, process 2 can read it, process 3 can write something, process 1 can read it. And so name pipes are an essential function in operating systems, and both Unix and Windows provide this facility for communication between non-related processes on the same machine. So that's all I had to say for today. We will pick back up on Thursday, getting into threading. Again, please make sure you're keeping up with the reading, and I look forward to seeing your submissions of the palindrome. So as usual, please stay healthy, please stay safe.